Welcome back to another lesson in physics. In this video, I'm going to show you a couple of sample problems using Coulomb's electrical force law. So here's an example problem that says to determine the electrical force of a balloon with a charge of positive 4 microcoulombs. The symbol here is micro, stands for 10 to the negative 6. Held at a separation distance of 0.70 meters from a second balloon of the same charge. The first step in solving this problem would be to draw a diagram. So here I have a diagram of 2 point charges, column A and B, and I wrote down that you have positive 4 Coulomb for A and a positive 4 Coulomb charge for B. The separation distance from the center is 0.70 meters. And I've drawn the forces acting on the particles, the force of A on B and the force of B on A. And these are equal and opposite forces. To the right is positive, and to the left is negative, so we know the force from A on B is going to be positive, and the force from B on A is negative, and they will have the same magnitude. The second step is to list the known values in the problem. And so for this problem, they gave us the charge 1 to be 4 microcoulombs. The symbol represents micro, and it means 4 times 10 to the minus 6 coulombs. And for charge 2, they gave us 4 microcoulombs, which is 4 times 10 to the minus 6 coulombs. And the separation distance is 0.70 meters. Junie, look here. The next step is to write the formula and solve for the unknown variable. The formula, Coulomb's formula equation is K times charge 1 times charge 2 divided by the distance squared. Since the formula is already set up for the variable we need, all we have to do is plug in our known variables and then solve. Here I've plugged everything into the equation. We have Coulomb's constant K, 9 times 10 to the 9 Newton times meter squared per Coulomb squared, times 4 times 10 to the minus 6 coulombs, that's the charge 1, times 4 times 10 to the minus 6 Coulomb, which was charge 2. Divided by the distance, 0.7 meters, and that is squared. So using some algebra, you see that we have 9 times 4 times 4 times 10 to the 9 times 10 to the minus 6 times 10 to the minus 6, and all the units brought over to the right, Newton meter squared divided by Coulomb squared, and there was the Coulomb squared on top. So the Coulomb squared is going to cancel with the Coulomb squared, and you're going to end up, after you multiply everything out, and by the way, for using the rules of exponents, 10 to the 9 times 10 to the minus 6 times 10 to the minus 6, you recall you add the exponents, so this is like 3 minus 6 becomes negative 3, and so you end up with 10 to the negative third, and when you multiply all this out, you end up with 293.9, and so move the decimal over 3 places to the left, and in your final answers using significant digits, you end up with 0.29 newtons for the electrical force. Here's a look at canceling the units. You'll see that we do end up with a newton because the meter square cancels with the meter squares on the bottom. Here's an example problem I want to do with you. In the problem before, we found that the force from particle A on B is positive 0.29 newtons, and the force from B on A is equal to negative 0.29. So in this new problem that I want to look at, what I want to do is double charge 1 to now be 8 microcoulombs. So essentially what you've done is say that Q1 is now 2 times Q1. And I just want to show you that this now becomes a proportionality problem, because if you look at the force from A on B, and you plug in 2 times Q1 but leave everything else the same, you'll see that the 2 comes out in front, and it's essentially just 2 times the force of AB that you got in the original problem, so it becomes 0.58 Newton. Okay, in this problem here, we're going to double Q1 and triple Q2. So you'll see, it's a proportionality problem. K is the same. You're plugging in 2 times Q1 for Q1 and 3 times Q2 for Q2. That becomes 3 times 2, which is 6 times K Q1 Q2 over D squared. And so essentially what you have here is 6 times the force of A on B from the original problem. Okay, for this last problem, example problem, I want us to decrease the separation distance by a factor of 2. So recall that the separation distance was 0.7, now it's 0.35 meters, which is half the distance. So you go into Coulomb's law and you plug in half the distance for the distance squared. And so that's half d inside the parentheses, which becomes 1/4 d squared. And if you do the math appropriately, you end up with 4 times KQ1, Q2 over the distance squared, which is the same as 4 times the force of AB. So it would be 4 times 0.29.